Okay, so we're going to get into a little bit today about testing a claim about a proportion, and we're going to use what's called a confidence interval. So we have this thing called a confidence interval. Okay, so confidence interval is like a set of two numbers, let's say like 1.75 to 3.68, that I'm guaranteed that some parameter about the population, either the mean or percentage of the population, you can use standard deviation, all these things, that I'm confident that it's got to have to lie on that interval. And usually I have a degree of confidence, and the normal degree that we tend to use is 95%. And all year you've been creating confidence intervals to some extent, but you just don't realize that. So today, we're going to make a confidence interval about a proportion, and we're going to use that to test a hypothesis. All right, so in our game here, we're going to say, let's take a sample, right? So John has taken a sample. He's sampled 200 people. And he asks them, do you like dogs? And he has found that 168 of those people like dogs. Now, we want to make an interval that we conclude with 95% confidence that the proportion of the people that like dogs is going to be on that interval. Okay, and in fact, if we do the calculations, we're going to find that this interval comes out as 0.789 to 0.891. So between 78.9 and 89.1 people in the population that John sampled like dogs. Okay, and he can say that that is certain to a degree of 95% given his sample. Now, how did I get that number? I'm going to calculate this by hand. You will never do this by hand in my class, but we're going to get there. Okay. So in John's sample, 168 out of 200 people, 168 out of 200 is 84%. Okay, that's the center of my interval. And I get that because of the central limit theorem. Because the central limit theorem says the samples have to be normally distributed, where the p-value, the p number, the percentage of the population that has the characteristics likes dogs, has to be near the percentage in the sample. Actually, the samples have to be near the actual one because there's a sense of central tendency there. So remember, we also have to say, well, like, how near does this have to be? And we found a standard deviation for the samples by taking this p times q over n, which in our case is 0.84 times 0.16 over 200, which works out to be 0.0259. Now, in the past, what we've done is we've said take 0.84 minus 2 times 0.0259, and then do that again with 0.84, not 584, 0.84 plus 2 times 0.0259. And we've worked out what those values are. And in fact, those values resolve to being 0.7882 is less than p is less than 0.8918, which, my gosh, these are really close to these values. Okay, and this is why the range rule of thumb works, because being 2 standard deviations away from the norm pretty much gives me something that's really easily calculatable, that's really close to the 95% confidence interval. But it's not perfect, okay? I'm going to clear out a little bit of the stuff on the top here to just kind of continue my exploration a bit. Okay, so let's get rid of this space. And we'll turn off that rectangle. And there we go. Okay. So how do I get the actual numbers for the 95%? The problem here is these 2's. These are really, really close to the right number, but not exactly. What I need is to be able to only have 5% error, right? Which means that in my confidence interval, I can have 5%, or part of the time I could be over here with my error, part of the time I want to be over here. So I want 2.5% of the error over there, 2.5% of the error over there, which means I want these numbers to be between the 2.5th percentile and this one would be the 97.5th percentile. So the 2.5th percentile you can get by using the invert norm on the calculator, and it happens to work out to negative 1.96. And the 97.5th percentile, you can work that using the inverse norm on the calculator, is positive 1.96. So if I want the 95% confidence interval with only 5% error, 2% below, 2% above, what I want to do is take 0.84 minus 1.96 times the standard deviation, 0.0259, is less than 0.84 plus 1.96 times the standard deviation, 0.0259. And if you resolve these two expressions, this is going to give me 0.7892 is less than P is less than 0.8908, which gives me that 78.9 and 89.1 that I started with at the beginning of all of this. You can look back in the notes. Those are the numbers that I gave you to begin with for the 95% confidence interval. So it's a little bit better than the range rule of thumb. Now this feels like a lot of work. So we're not actually going to make you do this. We're going to use the TI-84 calculator to do this. So let's take a look at how that worked. Okay, so this is my TI-84, and what I'm going to do is I'm going to go to Stat, and I'm going to go over to Tests. I have to be really careful here. I am working with a 1 proportion Z interval, which is way down here under letter A. This is not a 1 proportion Z test. I'm building a 1 proportion Z interval, and I hit Enter. Now, in my example here with John, we had 186 people. Out of 200, say that they like dogs, right? And we want the 95th% confidence interval. So I put the confidence level in there as a decimal, and I hit calculate. And bam, the calculator gives me that interval, 78.9 to 89.1, which is the exact answer that I got by trying to work it out by hand. Okay? So pretty simple stuff. The calculator makes this incredibly easy. So how do I deal with a hypothesis test? Okay, so this is only going to work if I have a two-tailed hypothesis test. Okay, so let's kind of work this from the beginning with a hypothesis. Here's my hypothesis testing. I'm going to say that 40%, it's got to be two-tailed, right? So 40% of likely voters in Maryland are going to vote for some candidate A for governor. Okay, so my claim yields two hypotheses. That the proportion of the voters for the governor for candidate A is going to be 40%, and the alternate is to say, nope, not going to be 40%. Now note, this is a two-tailed test because I've got the not equal. So you can only use the intervals if you have a two-tailed test. All right, so I'm going to take a sample. I'm going to sample 400 likely voters. And what I found is out of those 400, 164 are going to vote for candidate A. And the question is this true that 40% of our people are going to vote for this candidate? Well, let's get out the calculator. Okay, so I'm going to go back to the main screen. I'm going to Stat, Tests, 1 proportion interval, which is, oops, I want to be a test. That's why I'm not finding it. That's not good. Let's fix that. There we go. Okay. So we want to drive down to letter A here. I went past it. There it is. 1 proportion Z interval. I had in my example that we had 164 people say they were voting for candidate A out of 400 people on a 95% confidence interval, and it yields that between 36% and 45% are going to vote, which means that 40 is on that interval. So with respect to the hypothesis, I failed to reject the null because the null said 40 was going to work. Now, the null hypothesis in this case represents my claim. My claim was that 40% of the voters are going to vote for candidate A. So the non-technical way of saying this is that the data actually supports my claim that 40% are going to vote for this candidate. Okay, so I've failed to reject the null, which means I've supported the claim. The data supports the claim, and I've completed a complete hypothesis test. Woohoo! All right, so we're going to look at more of this in class. Thank you.